Okay, we're going to look at motion graphs. There's two types of motion graphs that we're concerned with. One's called the position versus time, and the other is known as the velocity versus time. And you can get a lot of information out of these two types of graphs. Graphing is really important in physics. Data doesn't mean much without a way to interpret it. Being visual thinkers, which we are as a species, graphs are probably the best way to look at any given data. And we are going to go ahead and start off looking at a position versus time graph and see what we can learn from it. So I'm going to draw some axes here first. Now when we do these types of graphs, we're always going to see time on the x-axis. And in this case, we'll see position on the y-axis. What's important to understand about any graph in physics, or actually in many other disciplines also, is that there's more to it than just the data that's plotted. So for instance, if I were to take the position versus time graph of a ball being thrown straight up in the air and then coming straight back down, it's going to look like a parabola. So the ball goes up and it comes back down. Here's the key to understanding graphs, is knowing what the slope means. So slope is, as you learned back in your math class, it's the rise over the run. Okay, it's the y changes over the x changes. In physics, this isn't just x's and y's. In this case, this is position and time. So if I take the rise, which is my y value, which is my change in position, aka displacement, and I ran out of room, so I'm just going to abbreviate. And my time is my x change. So I'm looking at the displacement per time. That's what my slope is equal to. We learned that the definition of velocity is it's your displacement per time. The slope of this graph is the velocity. And what you can see is that as we start off, we have our steepest slope, which means we're moving fastest. And as we go up, the slope is getting less, which means that my speed is diminishing, or my velocity is diminishing. When I get to the very top, my slope is 0, which means that my speed or velocity is 0. Now on the way back down, you can see my slope starts to increase, but in the negative direction. So what I'm getting then is an increasingly negative slope. In other words, this object, which I think I called it a ball, it's a ball, why not, is speeding up on the way down. And this matches our observations perfectly. When you throw up a ball in the air, it slows down till it reaches the top, and then it speeds up on the way back down. All position versus times graphs have this characteristic where the slope is equal to your velocity. Okay, so now we have a velocity versus time graph, and every data point tells us how fast we're going and in what direction at that given time. So here what I have is a line, it's supposed to be a straight line, use your imagination, that is got a constant slope and moving down like this. Okay, it's got a negative slope. Again, slope is everything when you're interpreting graphs. It should be the very first thing you think about. Rise over run in this case is velocity, or change in velocity, because these slopes are always changes per time, which happens to be the exact definition of acceleration. So this graph is able to tell us the acceleration by looking at the slope. Now we see we have a constant slope, which means we have a constant acceleration. This is a constant acceleration. It's negative. Actually, this is the exact graph of the same motion we had before. It's a ball being thrown up in the air and coming back down. The speed starts out positive. It gets less and less and less and less and less until it reaches 0 at the top, and then it comes back down with an increasingly negative velocity. If this is truly, a freely falling object on Earth, the slope would literally be negative 9.8 meters per second squared. Now, there's another thing that you can get out of velocity graphs, which is your total displacement. The way that works is you look at the area underneath the graph. If I look at the area under this section and I add that all up, if you think about what this is the area of a triangle. If you think about how we defined velocity. It was distance per time or displacement per time, and I'm going to skip the delta for the t. If you solve that for your displacement, you get that it's the velocity times the time. But this is not the instantaneous velocity. This is the average velocity. If I have a speed that constantly changes, let's say I throw this thing up in the air at 30 meters per second and it winds up at 0 at the top. The average over that time interval is 15. If I take that 15 and multiply it by time, I'm going to get my total distance I traveled. But if you think about the average velocity between 0 and anything is half. So essentially, I've got half my maximum velocity times my time. That's actually the formula for the area of the triangle. So the area of the triangle is 1/2 the base, which in this case is the time, times the height. Well, if you think of 1/2 the height as the average speed, you wind up with this guy. If I'd drawn this perfectly, this displacement would also be the distance traveled for this segment. I covered some distance on the way up, I covered some distance on the way down. Now when we have areas that are underneath the x-axis, we call those negative areas, and we call these over here positive areas. And so the displacement on the way up is a positive displacement. The displacement on the way down is a negative displacement. If you look at the total displacement for the entire trip, and if I'd drawn this perfectly, this area would be equal to this area, and the total displacement for the entire trip would be 0. That's exactly what we know is true for a ball going up and coming back down. It goes straight up and comes straight back down. Total displacement over the entire trip is 0.